running away and playing in the snow and making snowmen and everything. My co-chair, I think she took off to go play in the snow. I wish I could be doing that. So our speaker today needs no introduction for people who work on compilers and architecture. He's published tons of great papers in CGO. He had the Test of Time Award in CGO 2017. He's also served as program chair multiple times. And I expect those trends to continue. Keep watching this space. Today it is my pleasure to introduce Professor Michael O'Boyle from the University of Edinburgh.
Thanks for the great introduction. Thanks for staying around. I'm sure you had a great time last night in the museum. And we'll be playing with snow later on today. So I'd like to keep you maybe slightly entertained over the next hour or so, to give you my views on how the world's going to be changing for compilers, and maybe provoke some debate amongst us all. Okay. So to start off with, I'm going to try and ease us into this type of conversation and tell you some well-known things. So these are things that most of you will probably agree with. So, and it's time to set the scene for the later ideas I want to get across. Then I'm going to give you my view, and hopefully this is something you're not going to agree with. Maybe a touch on some pressure points we have as a community, maybe to make some debate. And then after that, I want to take this kind of a slightly polemical approach and try and give you some concrete results, some early ideas we've got on this subject, and how we think we take it forward. Then I want to drill down to next steps. Where are compilers going to be going over the next 20, 30 years, and why do I think that? And then I want to probably touch on a topic that's really close to my heart. Can we automate further? Can we actually keep on driving innovation and making compilers even more useful to the world? And then I'm going to summarize. So let's start with nice and easy. Let's talk about some well-known things. So what do compilers do? Let's have a look at what we've done in the past, what lessons we've learned along the way, and what's going to happen now. Compiler roles. So this is compiler 101 for most of you. Well, compilers actually are not just about languages and all the intricacies of register allocation. They're really about connecting algorithms to hardware. We're just the conduit to make things that people think of actually run on machines. Now that's a very noble idea, but unfortunately machines are a bit more complicated than that. They can only understand noughts and ones. Right? So you somehow got to take those great ideas and put them into noughts and ones so the machines can run them. So take those great ideas, we actually try to write human languages so that the programmers can put those algorithms into a form that's pretty similar to algorithms. And then our job really is to do automatic coding. This is what it was called back in the 1940s. It's actually automatically taking your program, which you've written in some high-level format, and put it into code that the machine can look at. Now the important point of view from this very simple view of compilation is that really kind of obsessed with the software-hardware interface. How does software actually communicate to hardware to get these things working? So I think this is the key relationship, and it's under strain with heterogeneity. The contract is breaking down between software and hardware. And what I'd like to do now is to say what's happened over the last 50 years. There's been much change, and what lessons can we learn from that change to help us have a much better future? So I'd like you to cast your minds back to the future. So let's think about 50 years ago. What happened 50 years ago? Well, if you remember, and there's a hint from your trip last night, there's a man put on the moon. For me, this is a personally massively significant significant event for me. I was 4 years old. I got woken up in the middle of the night by my parents and brought down to the TV to see some grainy images of somebody stumbling along their stone. And it was a fantastic moment in the space race. We've actually succeeded in putting somebody from space, human, on the moon. But the most important question is, what computational power actually was needed to do that massive event? Well, it depends on where you look on. It's really a few K of codes plus the power of a USB stick. So we did all those amazing things together back in 1969. The question is, what have compilers and hardware done since? Wow. Looking back into the 1940s, automatic code in your program was already around. We'd already done a huge amount of stuff. Much of the innovation is already taken back by 1959. By 1969, things have gone much further. We had optimizing compilers. Backhouse is a Fortran compiler, which actually generated really efficient code. It's automated not only coding but programming now. And we had really the early starts of parallelization. Carpel Winograd paper in 1967, which is uniform recurrence equations, which is kind of the basis, if you skew it one way or another, as the basis for polyhedral compilation and polyhedral optimization now. So by 1969, we already achieved a huge amount. Since then, as you all know, we've seen a real revolution, particularly in the hardware space. If you look at the last 50 years, from ish, so say 1971 to the present day, you've actually had about 1 million times increase in performance of hardware. And we all know the reason for that 1 million times improvement. The reason is Moore's law. We've seen exponential growth over this time. So year on year, we see an increasing performance improvement. And this performance improvement is what's really which underpins computing. It's no exaggeration to say that 50 years of Moore's law have really enabled the digital age. They are the basis for all the software we see in the world and the investment in it and its growth. So, hardware's had a great 50 years. The question is, a compiler writer is, so what have compilers been up to since 1969? What have they been doing in the last 50 years? And I'm afraid it's a story of actually not too great at the beginning, and hopefully a much more positive future. So let's go into that a little bit in detail. Compilers redux. Well, I worked in parallelization for many years. Just done a great work out of Illinois, the founders of that, right up to the mid-90s. And actually, in fact, automatic parallelization, as it was phrased back then, that's a big caveat, really failed to impress the community. People didn't buy it. So I'd like to come back to that story in a second. Architecture's riding Moore's law is high. It's actually improving performance year on year, and your chips are getting faster and faster. So parallelization is not even needed. So that compiler effort to get parallelization both doesn't work, and you don't need to worry about it, because in 18 months' time, you can get double the performance. Compilers disappoint in other ways, really. They had the big memory wall problems identified back in 94, 95, and really, we've really failed to do much impact on solving that problem. We now see some 3D stacking and other types of hardware technology, but our role in saving the world is pretty small. So in fact, you could put it this way, that compilers have little to offer. Let me make this a bit more personal. So I wanted to work in parallel computing because back then, Cook was saying, optimizing of scalar machines has already been done. So it's already done in 1990. So I thought parallelism is the place to go for me. Then I started talking about how to do automatic parallelism with some of my colleagues in Manchester. They said, we don't want you to do that. That's the fun bit. Stop it. So scalar stuff's already done. Parallel stuff I'm not allowed to touch. It got a little bit worse. Who cares about parallelism? This is actually a review I've got from 1997. Who cares about parallelism? It's all been done before. What about Java? Java's cool, right? Now, we may actually want to put Java now, but machine learning, whatever you want to put in there. There's definitely always a hype, right? So it's all been done before, nobody cares about it, let's do the new stuff. My favorite one actually is from a conference, which I'm not going to mention. This conference is for smart hardware and dumb compilers. There's no place for your smart compilers here. It was slightly tongue-in-cheek, but the point was being made. We don't want to hear what you like. We don't want to hear what you've got to say. And my favorite one of all time, this is the entire review of a conference back in 2003. I don't like this. So you may actually over time actually have those really negative reviews. We've had them as well over the years. That's all you can say is that if you live long enough, you get to stick them on slides and don't get the audience to empathize a little bit. So compilers having a hard time. And even more, this famous Probst-Things law. If we assume that useful compiler optimization happened in the mid-60s, not 69, then we've been given about 3.6% improvement year on year. That's what we've been doing as a community. While the hardware people already have given us 60% a year. So, it's pretty depressing. Why are we still here? Why haven't we just got away and done something more useful? Well, actually, fact, while we didn't solve the memory wall, there was a crisis that did actually help us, and that happened back in 2005. It's the power wall. As the architects will tell you, they simply couldn't stick enough more and more transistors into a certain amount of space because you couldn't afford the heat. So the only way out of this was parallelism. You need to have lots and lots and lots of them. So from 2005 onwards, we see a huge increase in the number of cores. In fact, Chuck Moore from guy AMD said, actually, the industry is in a bit of a panic at the moment. In fact, you need a PhD to program these things. So maybe compiler people can actually have a role once again. And actually, I'd like to say 2005 onwards has been the comeback years for our computer compilers. Single core hardware is beginning to stall in terms of its performance. It alone is not going to give you the scalability year on year. In actual fact, architecture cannot do it alone. You need compilers into the mix. So, since then, language and compilers have been key to lots of different frameworks, such as MapReduce and others, which working with smart compiler and runtime technology can actually help you exploit that parallelism. In actual fact, I said that automatic parallelization failed. In actual fact, since then, we've actually seen a renaissance in this area, kind of what I call a dynamic auto-parallelization. By using profiling, ints, pragmas, help, whatever you like, you can actually parallelize code. But there's much, so there's been a great renaissance in this area. So it's been the comeback years. So what are the compiler lessons that we've learned along the way? Here are the lessons I like to say. In theory, everything is nearly impossible. In practice, we seem to be able to do a lot better than that. Okay, so you look at any compiler book, most of the problems are MP, you have to look at some heuristics, it's really quite complicated. In actual fact, whether a code runs fast or not is undecidable, it's really hard. But in practice, humans manage. We get around these problems, we find approximations, and they often work as well as the theory says is optimal. We often use static analysis. We have to analyze code to work out to prove things are safe. Don't worry about that. Just try dynamic profiling. Don't worry about all those things that could occur. In fact, in practice, they don't occur at all. Use profiling to give you information. We tend to obsess about proof, making sure these things are actually absolutely correct. In actual fact, we can use statistical evidence to say, in practice, that it's an important thing or not an important thing. We've moved from a place where we used to have handcrafted heuristics based on naive assumptions of the machine, and we just use machine learned models now. Rather than worrying about guaranteeing things are safe, things are proper, things are okay, we just speculate and fall back. In some sense, in a very big sense, we've moved from a maths-orientated culture, which is highly conservative and wants to prove everything, otherwise it says no, and we take a leaf out of the hardware group. We just have a hardware culture, which is a lot more radical. Try and see. If it doesn't work out, roll back. And I think those are the big changes we've seen over the last 50 years. So let's hammer home this point. I want to make a little dig. This is a compiler-writer's model of view of the world. If I just get those blocks just the right shape, I can solve my system. In actual fact, unfortunately, systems are a bit more complex than that. They're more like this. So rather than this fictional world we try to optimize for being nice and simple and solvable, in actual fact, reality is a lot more complicated than that. And this is the reason why myself and others have been pushing a different way of looking at things over the years. We've moved from analytical models, which are correct but based on fiction, to machine learned models, which are complex, maybe a bit clunky, but that actually reflects reality. So, the real message I'd like to say over the last 50 years is really, we have to think differently about the problem. It's not just automatic coding anymore, there's a lot more going on there. We have to investigate new tools and methods. And the remainder of this talk, I'm going to try and explain what I think those new tools and methods may be. So, the big question is, what now? Well, I think we all agree, technology scaling is coming to an end. Although we can theoretically put more transistors in, we can't fit them in anymore. The first thing off is power is the problem, now it's scaling. And this slide I stole from an Intel website somewhere, actually showed that eventually, everything's going to plateau out if you're not careful. So really, Moore's law is coming to an end. And the consequence of that is that the hardware and software contracts that we've been bound into for all these years are starting to break down. So what do I mean by breaking down? Well, the digital age has really been based on a contract, an implicit contract. And the contract is, hardware may change under the hood, from a 1971 processor to today's one. But the hardware-software interface remains constant. The way you program those machines doesn't change, even though they change radically underneath. And that's really important for software. It means that you can invest. Sorry, I keep pressing my button too much. There we go. Software which is written today is guaranteed to run tomorrow. That means you can spend time writing your code today because you know the effort and expenditure involved in writing that code is actually going to be paid back over time. And this has actually been the basis for a multi-billion-dollar investment in software for the last 50 years. So this hardware-software contract is breaking down. In actual fact, if you watch any politics over the last, so we say 3 or 4 years in the UK, it may sound familiar, right? So sometimes we've got our own type of software hardware Brexit. Well, I've been assured by my politicians at home that it's all going to be okay. Subject to some details I'm not allowed to divulge with you. I'm going to spend most of my time looking at a slightly easier contract to fix. Technology trends mean that hardware specializing in heterogeneity is inevitable. So rather than our handy Turing machines we're used to at work, where we have our infinite tapes and go backwards and forwards, which although are guaranteed to work, are a bit slow, we're actually moving now to, say, much more, should we say, specialized devices, such as Google's tensor processing unit. This is great. If you've written really bad software really slowly and you use this and it fits just right, you get up to 100,000 times performance energy gains, give or take an order of magnitude. But there's no free lunch. Software cannot fit on this new hardware, right? It's given us this new heterogeneous crisis. Software can't fit, then there's no point generating new hardware. Hardware's going to stall as the software can't fit. So you've kind of got this deadlock. You've got this potential technology that can't be exploited, so there's no point building it. So my answer to that is we need to rethink the contract. So how are we going to do that? Okay, over the next couple of slides, I'm going to try to give you my view about how we can redo the contract, what that means. And then this may sound a little bit fanciful at times, but then I want to drag it back to something a bit more real, get some concrete initial results, and talk about the next steps. So my view, what is my view? Well, really, we have this heterogeneous hardware zoo out there, all these processors, all different types, and we really want to be able to tame it. So we want to get our application code running on those different devices. So the question is, how are we going to do it? I'm not the only other person in this room, probably every person in this room has thought about that question. How do we get code to run on these new devices? Well, there's a language approach. Many of my colleagues, particularly in the fifth floor of my building, say this is the way we need to do things. What you need is just a really clever parallel program language, right? Which we all agree on. So once we've agreed on that parallel program language, the user simply has to write every single application he ever had in this new language. Then we just have to write a new compiler for this new language to every potential hardware that we have now and in the future. And then we have to have some smart runtime glue to make sure all stuff works. Most of us would love this to be the case, but in fact this is kind of like a unicorn. I don't think it's ever going to happen. There's never going to be a language that all these computer scientists agree on, and certainly never going to get all the programs to rewrite it, and we're certainly never going to be able to optimizing compilers to get the best out of every single bit of hardware. So whilst this is attractive, I think it's doomed to failure. Now, a much more attractive fashionable approach is the DSL approach. So you say, oh, okay, languages are too big and clunky. What we really need is smart, smaller languages that are nearest the application level and can be efficiently managed and hit your hardware. So this DSL can run on lots of different bits of processors out there. You don't have to worry about that, you just rewrite it. Well, actually, in fact, now it's actually even worse. So each of your programs has got to rewrite their application in not just one parallel language, but multiple ones. Furthermore, you don't know if those languages are going to be around in the future. Furthermore, you don't know, and when they die or they're no longer supported, you have to rewrite your code, re-back engineer it. And you have to hope it's actually going to work on your next machine. So while this DSL approach is very attractive, I think it's doomed for failure as well. Not very positive. So, what I want to do is make the good observation, following observation. Good performance is hard to get on these heterogeneous hardware, even with well-defined programming languages such as OpenCL and CUDA. Okay? In fact, it's so hard to get that they generate a whole bunch of GPU-accelerated libraries. These are libraries that work on accelerators because CUDA and OpenCL won't give you the performance. So here's the insight I'd like to share with you, which you may disagree with. Rather than building a new compiler for every new platform, why don't you just pick the best library or API or DSL that's on that platform and just fit code to it? So in other words, libraries and DSLs are the new ISA. Okay, so it's now the compiler's role to fit code to these ISAs. So let me show that in a cartoon diagram. So we have your legacy program up there, and you've got all your processors out there. Each of them have got a wide blue interface, which means they're kind of Turing complete, or they're a bit narrower, which means they're a bit more specialized, faster, but not Turing complete. What you tend to do is you look through your program and say, actually, there's bits of the code I can partition up and map down. So So typically if you're using a GPU, put some on the host code on the multi-core, you stick the rest on OpenCL on the other side. Okay? That's how we typically program a heterogeneous system at the moment. Why are we looking at it slightly differently? Let's say each of those bits of hardware has a DSL or a library or an API exposed. And these libraries or APIs of DSLs are things such as Poly, 3D building blocks, BLAS, Milk-Halide, whatever you like. They're just interfaces. And they perform specialized and efficient implementations. And what you've got to do now as a compiler writer is just fit those to your code. What bit of code looks like BLAS? Just do that. What bit actually looks like Poly? Let's do that. What looks like an FFT library? Let's do that. In some sense, you can look at it this way. In the olden days, we had an ISO called x86, which was a long way from the program. It was great, in fact, it stayed still, but it's very narrow. So you've got to try and talk about the programmer intent on the programmer side by this very narrow pipe. So in other words, there's a big distance between the semantics of the program and what was running on the hardware. However, it was stable, it was good. And the compiler's job is to go from programs all the way down to x86. With the advent of OpenCL, you can actually abstract over hardware a little bit. But as we've seen in the previous diagrams, although the program to OpenCL interface is smaller, you get poor performance. What I'm suggesting is something different. We do the following. We just say that these libraries and interfaces exist, and it's our job to take a program down to those little libraries. Now we know those libraries or APIs or DSLs are going to be well tuned because that's what they'll be ported by the vendor. Our job is now just matching it. So, put another way, this new ISO is nearer to the algorithm, is likely to be a better fit. However, it is now complex, changeable, and very, very bumpy. It's no longer this nice, stable interface. So how can we manage that to change? It's a big question we have to answer. And also, how do you match all these different ISOs to the code? In fact, we may find that actually, as the number of number interfaces increases, they can match all different bits of the code. How are we ever going to possibly manage that kind of complexity? Well, actually, it's relatively straightforward nowadays. We just use machine learning. Run a bunch of experiments, work out which is the right one, and it matches. Okay, I've glossed over some details there, but I think that's a viable way forward. When we have a problem, we just generate data and learn a rule. Okay, now that's a very compiler perspective of the world. But I want to say actually back to the hardware people in the audience that this approach really frees up hardware creativity. So it's a way of really looking at the contract which actually makes hardware life a lot more fun as well as compiler life. Let's see what I mean by that. So this is my view of how hardware designers think. Right, so please suspend belief for a little while. Right, I want to build a bit of hardware out there. I've got all these cool ideas out there. I don't know which one I should build. I think it'll go dead fast. But I don't know if anybody ever program it or use it. It's a problem for me. Which one to pick? Okay. Well, let's assume you've got a space of interesting programs you want to actually match your accelerator to. The question is, which one should you build? Is it going to be useful and more people will use it? Is it actually going to be worth the investment? Well, given now we can match interfaces to code, we can do the following. We just say, rather than building that bit of hardware, just give me the interface of that hardware and what it supports. And performance or cost estimate. How likely is it to give you good performance? Once we have that performance estimate, we then can actually, using the technology that matches interfaces to code, can give you a coverage, i.e. how much of that bit of hardware actually matches the code out there that's of use to you. So you can actually do a performance versus coverage metric. So you can trade off the amount of performance you're going to get to how likely it is to actually hit real users' code in a software base. Then, you just learn which is the best interfaces, that maximizes your actual code base, and you go work out, actually, I need to build this bit of hardware and that bit of software. Once you've done that, you go a bit further. You already see the approximate computing, that we can actually approximate what code does as neural networks. We can do the same thing with the interfaces to hardware, and if we're smart, we can actually match code to hardware, all with no hands attached. Now that may seem a bit fanciful at the moment. I'm going to come back to this in a little bit and show that actually I've done some work we've been investigating and make this possible. So, now let's talk about some concrete results. So, some work I did with my student Philip last year, we looked at idioms and constraints. What we did try to do is describe the interfaces that exist in libraries and in hardware as idioms. These are typical things that people have in their programs. We try to encapsulate them as constraints and try to match programs to hardware. So what we're really trying to do in this piece of work is detect code structures that match interfaces. The interfaces you're interested in are APIs such as CLBLAST, Sparse, or some, and the actual Halide, which is a stencil DSL, and Lisp, which is kind of data parallel and functional programming language. And we want to say, okay, these are fast bits of code out there. Can we actually match them to the program we have? So what we did, we invented an idiom description language which describes things such as stencils and matrix multiplication. We then translate them into constraints, stick them into LLVM, find the bits of code that match the hardware, replace it, and run it. So that's the high-level view. Well, we're making this, before we actually go down to do any of these experimentations, we did the following important thing, which I try to get all my students to do. Don't go around solving a problem unless there's some evidence that a problem exists. So in some sense, do these APIs, are they of any worth? So we actually ran through the Parboard and ASParallel benchmarks week. We found out that these stencils, these APIs, these DSLs, these idioms did exist. Also, they were of significance to a large number of applications. So they actually were the dominant piece of computation inside them. So in other words, if we were able to speed them up, we're likely to get some performance. If the answer was 1 or 0 all the way across the board, we would not have done this piece of work. So that's another lesson to learn. Don't do it unless there's some benefit out there. So what we came up with is a language definition called IDLE. It gets matched to written as constraints. We then stick into our own SMT solver inside our LLVM compiler. We go through, we translate it into our important bits into the library calls or DSLs, and we stitch it back together and run it. So let's have a look at that in a little bit more detail. We've got the input program language, it can be C, C++. We've also done a Fortran port, which believe me was not much fun. And then what we did, then we had to describe our idioms or our APIs in this description language called IDLE. It goes into the red box, and then it finds the necessary match, cuts out the code and links it with the vendor library, or more ambitiously, cuts the code out, sticks it to a DSL domain-specific code generator, which generates itself the library, which we then link to. If you go inside the box, it's a little bit more complex. Whoops. Actually, in fact, this program, we take it into, and we put it into LLVM IR. We do some optimization to normalize it. We then translate that IDLE program analysis to constraints, stick them into our constraint solver. We find the bits that match. We then go and actually generate library calls and replace that code with a library call or calls the code generated by the code generator. Okay, that sounds like magic. How to work? I'm going to show you a very simple example. Say you want to do this really awesome, to use an American phrase, optimization, right? You want to be able to do, you want to say, hey, I don't want to do 2 multiplies there, I can factorize and just do 1, right? So it saves the whole operation. This is sort of a bread and butter for compiler writers. Well, what we want to do is this common factorization in our language we express like that. That alone will do everything. Really, it's just a constraint language. The key point is that the common factor you're looking for is either it's in the first or second element of the left bracket and the first or second element of the right bracket. If it's common, you can factorize it. So let's look at an example. Here's an example for our piece of code. The cunning amongst you realize in that as d is equal to a, there's a common value there inside there. But though you can't syntactically see that, if you stick it through LLVM, you realize in actual fact it does some constant propagation, value propagation. And it works out in actual fact, hey, A is being used twice. You run it through our system, and it realizes that there's a common factor, A is common in that expression. You can then replace that piece of code with the right-hand side. Great. Well, great, yes, but not really. I mean, you spend a lot of time, a huge piece of technology to do something that's already implemented in LLVM, isn't this a waste of time? Well, the key point is that you can do a bit more than just do common factor expression elimination. That, you look at matrix multiplication. So matrix multiplication can be described as these set of constraints. Stick them into the compiler, it goes through your code, finds the matrix multiplication, cuts it out and sticks them called to BLAS instead. But it's not syntax matching, which is kind of an old approach to this approach. So you can write your code in many, many different ways. I'll give just 2 examples there and give you pointers, whatever. And because we do it at the IR level, we do normalization, we can actually discover many, many equivalent things, which are equivalent to matrix multiplication, written in a variety of different ways by programmers. So it's not syntax matching, it's semantic matching. Well, you may argue, actual fact, that's not great. I mean, there used to be a flag I remember on a Cray compiler that may do that. It didn't, but it may be some people's memory they can remember those stories from the past. So we just think something a bit more ambitious. We want to look at sparse matrix computation. So we can do the same thing with sparse matrix computation. We can just write it as a bunch of constraints in that red box, run it over your program. It finds the appropriate thing, cuts that, and puts in a call to the QSparse library. And then, but you actually go beyond this as well. We've got wider applicability beyond just this library interface. We actually do polyhedral detection in about 45 lines of code. So that allows you to say, hey, your bit of code could be optimized by poly. Here's a good way to do it. So, how did it work out in practice? Well, in fact, we actually ran it on NAS and parallel and hardware benchmarks. You can find many of these stencils, many of these APIs, many of these idioms. And we actually found that in many particular cases, there's an awful lot of the code that actually was actually at its heart had a kind of stencil or a sparse matrix modification. So we just looked at those applications, and we showed, actual fact, we've got speedups from the very modest 1.1, I'm not going to do any application here, actually up to 250 times, that was the SGM example. Actual fact, the truth is we got much bigger than 250. But the number was so big that the reviews wouldn't believe us. So what we did, we tried to optimize the baseline to make sure the number came down to 250. So it's actually able to automatically find and exploit parallel idioms in standard benchmark code. Let me also say these ICC, great compiler from Intel Poly, a very great compiler inside LLVM. When it ran over these benchmarks, on average, gave a slowdown. So here we have a simple technique to give you great performance by leveraging what libraries already do for us. So they give us some view on speed up versus hand parallelized code. This is a much harder test. We found we're competitive in 6 cases, but the user has to change the algorithm to create parallelism in the other ones. If we actually change the algorithm and get the parallelism, we got the same performance as well. So it's pretty robust, even compared to human effort. Okay, so I've talked about some well-known things, what we may or may not agree with. I've talked about my view of how we can go through matching code to hardware by using this constraint-based way. We're looking from bottom up, gave you some concrete results about the initial story along the way. The question is, what are the next steps in this story? How can we go further and compile this for the next 20, 30 years? Well, I want to look at an example of what I call extreme heterogeneity. So look at an FPGA. This is a device that allows you to actually try all types of, explore all types of hardware, heterogeneous hardware. You can change it every day of the week and it's a different device. So it gives you the opportunity to explore many, many different bits of hardware that will fit your code perfectly. However, getting your code to fit such hardware is tricky. And this is the area known as FPGA compilation or hardware synthesis. In a nutshell, you try to go through the code, maybe using separation logic or some other technique. You try to find bits of the code that are likely to be accelerated and worthwhile doing so. You then go and cut out slices of the pieces of the code that you think will give you some performance. You then try to match, then you actually try some synthesis path that goes all the way down and generates the FPGA. And if you're lucky, you get some great performance. So, in some sense, you can think of FPGAs as being the ultimate software-defined hardware device. They allow us to define hardware to fit software precisely. They're great. They allow us to specialize hardware to this program. So in other words, you don't have any wasted circuitry doing dumb stuff. It's just stuff that's perfect for your program. So it's great. However, it's expensive. Actual fact, trying to go to synthesize bits of code to FPGAs can take a long time. And if actually it's expensive, sometimes it fails. If you try to have a more aggressive design, you spend a couple of hours trying to synthesize a bit of code, and it just doesn't hit the structural limits. So and to be honest, you're not going to use this in JIT compilation. You're not going to do a JIT FPGA on the fly to see whether you get the code running. So it's expensive, and it has another problem as well. It's inefficient compared to hand synthesis. If you really cared about accelerating a piece of software, you can actually do an awful lot faster by hand. A bit like the automatic coding problem back in the 50s. Instead of, so we're, in some sense, the automatic coding of FPGAs is not as advanced as our automatic programming hardware in the ASIC world. And here's probably the real killer in the end. If actual fact it really did work and fit on the FPGA, and it really mattered to you, if you built an ASIC, it'd go a lot faster. Right? So there's a real problem there. So FPGAs provide the flexibility of designs software-defined hardware, but in some sense, they don't, if they really work, they might be better off sticking ASIC design anyway. So what I've been describing is actually the exact inverse of that. I mean, this idiom actually is trying to say, well, we've got some hard interfaces, let's fit them to software. In some sense, it's hardware-defined software. That's exactly the inverse of that problem. So what's great about it, it gives efficient implementations. We assume hardware designers are not going to build an ASIC that does a specialized heterogeneous function, if in actual fact it doesn't do it efficiently. However, there are some drawbacks I'll have to admit. In particular, a good match is not guaranteed. If it doesn't fit your program, tough, you can't do anything about it. If you have the FPGA there, you can retune it, here you're stuck with it. Now I want to look at these two different worldviews and see whether you can do something that's more constructive. Well, we think there's a co-design cycle. Initially, you start off with some flexible hardware. You then compile using FPGA synthesis down to this hardware. Over time, you find useful bits of hardware that are persistently used in your synthesis route. You can then harden them into ASICs, which then you know of use because you've seen them compiled before, and you automatically have a technique to match it back to hardware. So it gives you a technique to go round and round in a circle, where you can have software and hardware innovation on both sides without that ISA constraint that's been holding things back all this time. So in other words, I think this technology provides an opportunity for both sides to have to be creative without the kind of ISA contract that's been keeping us back for 50 years. So, one of my passions is to try and make things automatic. I can think about it, why can't I just automate what I think? So can we automate all this further? So, whilst I like the work we've done so far, it requires this idiom description now, which is a bit clunky. What happens if you don't know how to describe things? What I want is that blue box. You just throw programs into it, you throw hardware in there, you leave it for the weekend, and it comes back and it automatically applies programs to hardware, no hands involved. Right? So what I want is to learn what hardware does and match software to it without any work. Now, that sounds like fanciful thinking. Well, actually, there is some techniques out there that maybe allow us to think about that. So what we really want, to go is a constraint language on the right-hand side, and on the left-hand side, we have our interface we're interested in modeling. It could be a piece of hardware, it could be a library API. It's something you want to know about. I'm going to match that to IDLE, because IDLE allows us to match to code, and that way we can match our interface or hardware to code automatically. So how do we get from the red rectangle to IDLE? Well, there's some work in other areas outside my comfort zone called program synthesis, which I'm trying to learn quite quickly. What you can do is interrogate and synthesize what goes on. So you send it over examples, it gives you back results, and over time you can actually create a program which has the same behavior as the thing you're modeling. You do that enough times, and then you can create different versions of that interface, multiple different programs. You can also do transformations on that program, create thousands of equivalent ones. These are all different ways of describing that interface. Then here's the clever bit. You can then use induction or graph matching to find out the greatest generalization of all those. And actually, in fact, you can do it in a way that actually gives you constraints. So by generalizing those programs, you can actually get a constraint language, which is in fact IDLE. So here's a kind of a stepwise diagram how you can go from a hardware you don't know much about to constraints that match hardware and software. Now, the question I would ask is, well, this is a nice little diagram on there, lots of arrows and colours, but where are you and does it work? Well, we've actually done some work on type-directed sketching. Sketching is a well-known technique in the program synthesis world, where you actually have some priors over your expected behavior of hardware. Our prior is we expect things to be control-intensive, and we have these priors as possible bits of code that could match hardware. The reason being you don't build hardware to do insignificant computation, you do stuff that's going to have some complexity in it. Using that, and the type of the interface, i.e. the input-out behavior, which you have to have, we can then actually learn all the BLAS 1, 2, 3 interfaces. We can learn how to sparse BLAS interfaces. We can actually learn cryptography as well. We can do a whole bunch of learning at the moment. And we use it by our generalized induction technique. So that's our current state of the art. And what we're hoping to do is go beyond that and automatically learn all types of idioms. And generally, here's the long-term goal. Can we learn what a programming language is, semantic are, just by description and syntax? So, that's one way to automation, this program synthesis induction constraints. There's actually another way to exactly the same place. And that's machine learning, distillation and matching. We can use machine learning to describe what an interface is. You have input-output behavior, you build a model, that's the model hardware. You can distill it down, which means you build a student network which actually has the essence, you shrink it down to something small. You do the same thing on code at the high end, and then you do a Euclidean distance type thing to show these things match. So those two are exactly the same idea, but in completely different communities' ways of thinking about things. And what's nice about that, there's a duality on there. So what you're doing in program synthesis machine learning, there are two sides of the same coin. They're both pros and cons. They're not always great at different things. Machine learning is approximate, gets there quickly. Program synthesis is slow, but it's accurate. Can you use the two together? So, earlier on I tried to describe what I thought was the key things that have changed in 50 years of compilation. So the key question I think is, what's the new things, what's going to happen next? I spent a bit of time to describe this. Some of these are things that you probably find are obvious. Some of them are a bit more speculative. Well, machine learning is really possible, popular at the moment. DNA seem to have amazing power. Well, why don't we just use them to learn everything a compiler does? You just give them enough examples, why can't it learn it? Why can't we just make us all out of work? Well, I think that's a ridiculous idea. You can go so far, I don't want my job online. No, okay, maybe not, all right. Because of course there's accuracy there. But you can go quite a long way. For instance, there was some work recently, I can't remember the reference, but actually, in fact, you can automatically learn deassembler. So you just stick a program in, lots of examples, lots of assembly at the end. You've got prior based on the structure of that, you think it's a tree transducer type thing, and then it learns a disassembler. Okay? So you can learn a disassembler, why can't you learn an assembler? Or a code to thing, a generator? Why not? I think also we live in a world now where, you know, when you want to find out an answer to a question, what do? You Google it, right? You're thinking. Why? That's a very clever way of describing crowdsourcing. You just go look out there. So if you want to actually do an automatic parallelization of a bit of code, if somebody else has already done that somewhere else, why don't you just go and search for it? So crowdsourcing is the new type of profiler, which uses all that information out there to guide what a compiler does. Don't keep reinventing the wheel. I don't mean crowdsourcing as someone sitting down typing into Google. I mean, can you automate the process? To do that, we're going to need natural language process-based approaches, which are able to scale over large corpus of data to find structure to match. And we need to think of programs as really corpora, and can we exploit that in our optimization? So I also think it's going to be happening. The type of program synthesis I talked about is kind of thing called deductive oracle program synthesis. I think this is going to be a strong tool to be able to actually learn what the systems do, and it gives you a program which we can reason about. And I think, for me personally, now I'm really interested in exploring the duality of synthesis machine learning and work out when one's useful and when the other isn't. So, summary. So what do I think? Well, I think to solve the heterogeneous crisis, we need to look at the role of software and compilers differently. We need to think of really where we have hardware-defined software, but the compiler's role is to match the hardware to the software by shrinking the APIs and managing that complexity. If we could do that, then we have hardware innovations available without ICE constraints. We're no longer chafing with one person in control and the other. You can unlock hardware, you can unlock software, they can be created together, and we have a system that brings them back together again. But really what I think we're trying to make it a sort of slightly grandiose things, we need to think differently. You know, every time we have a crisis or get stuck, history shows that we just need to change the way we look at things. We need to look at different tools and different systems, and maybe we can make some progress. So, back in 1969, it's been a rocky road since then. Hardware and software haven't always been best of friends. But maybe we can work together and be first person on Mars. Thank you very much. Okay, so that's a very good question. In actual fact, when I show examples, I tend to show source. The trouble with source is you have very small perturbations in the code, or large ones, where look very different, when in actual fact they are semantically the same thing. So we want to get away from that syntactic structure, like for instance if you've used different types of control structures with the same idea inside them. We want to get away from that kind of syntactic down to semantics. Now, LLVM has got more semantic equivalence at that level than a syntactic level. Ideally, we'd like to go beyond that and really understand what the actual code is doing. But if you do it at a syntactic level, then very small changes or large changes, which have the same underlying meaning, get lost. I'll give an example. If you look at the DSP stone, which actually uses pointer-based arithmetic to do base multiplication, and then you look at a Fortran representation, they're a million miles away, but they're the same thing under the hood. By using LLVM, we're able to find that.
Okay, so for your idiom recognition, do you have some data about false negative and false positive?
Yeah, this is a really important point. So, in actual fact, I didn't go into that. In actual fact, we have different types of constraints for different scenarios. We have ones where we're not worried about false positives, one where we are, and ones where we're not worried about false negatives, and ones where we are. So you have like a ring of constraints, and depending on the circumstance, you have you can have a mess and a maybe type set of constraints. In the examples we had no false constraints, false positives. However, I'd be a fool to say that's not going to happen in practice, okay? Only in experiments we refine. If you look, the nice thing about that is as you have more and more data available, we can actually refine the constraints. So no, we didn't find any in this example. That doesn't mean to say that we won't have it.
Okay. Thank you very much.
So, I have a question. I didn't hear the original question, so this may be the same question.
Okay, sure.
But, so you said, yeah, you're doing semantics.
Yeah.
But it seems to me that you're doing semantics by a translation into LLVM.
Mm-hmm.
So, but at that level, were you looking at the syntax of LLVM? You're
Well,
doing syntactic matching.
In some sense, at that level, I'm trying to say is that because we do normalization to a particular form of IR, okay, so we actually say we go through a whole bunch of processes to make some things that look syntactically different will be semantically nearer the IR. Well, I agree, it is possible to write, we say, examples which a human would know are similar, of course, but then what we've done is the ability, if that's the case, we can actually have lots of different equivalent ones and we can generalize them, so that thing of generalized reduction at the end. By graph matching is something we're looking at. So you can actually have a slightly greater scope of things that are probably equivalent but not guaranteed. So you can generalize it a little bit more. And of course it's ongoing to see exactly how general you should be and how narrow you should be. And I don't know the answer to that, but that's something we're investigating at the moment. But you're absolutely right. Yeah.
Hi, excellent talk. My name is Krishna Nandivara from IIT Madras. Wanted your take on the following. If you look at PLDI, POPL, CC, CGO,
Sure.
like for last K1, K2, K3, K4 years,
Yeah.
you have many papers,
Yeah.
let's say only on non-parallel serial programs, showing 10%, 20%, 30% at least. No one talks about 3 to 4% improvement.
Yeah.
With so many papers, all claiming 20, 30% improvements,
Yes.
and we see such low overall gains.
Yeah.
What's your take on that?
That's a tricky question. So is there any funding company organizations in the area? No. Well, I'm sure all those 20 and 30% are really honest at the time they get taken, okay? But of course it all depends on the experimental setup. I also think, in some sense, we do enough of cherry picking of our benchmarks in our community. For instance, why would you go around to show me a paper that shows it gets really bad performance with database code? No, and all your results are database code. So I think we tend to actually, a truer answer would be, we're good against good performance improvement in areas. And what I would suggest is we need to have a slightly more flexible approach where we use different techniques for different types of applications. So if it's looking like linear algebra code or affine code, polyhedral analysis is perfect. If it's looking a bit more complex, then maybe a different type of technique. So I say, actual fact, they potentially could all work, but not one of them is ever going to give you the 20% for everything. Okay, thank you. Yep.
Thank you for the talk. The discussion about matching equivalence on LLVM
Sure.
canonicalization resonated with me. Now, I think we are using LLVM because it's successful, it's there.
Sure.
But it's also maybe not the right IR.
Mhm.
I wonder if you had thought about, like, 10 years from now, what should be the best IR in the compiler so that to support better the flow that we envision?
That's a tricky question. So let me try to unpack that. Right. So one, yes, we just picked it because it was there, it's popular. my PhD students know it. 2, it's very well designed, engineered, it seems to have a long set of legs. But you may have said the same thing about, say, GCC 10, 20 years ago. I'm not particularly attached to any particular ISO, I just want one that kind of works we're going to use. Because there's so much infrastructure around it, it's the obvious place to start. Now, the deeper question is, what's the right IR? I really don't like that question. Why don't I like it? Because actually, I don't know, right, what the right one is. I think actually, as we explore and we find that we're unable to match and find things, maybe there will be pressure to put more things into the IR. Certainly, if you look at LLVM, there's been a movement to put maybe parallel primitives into the language to talk about parallelism. I don't know. I don't think I'm the person best qualified to say that. Hopefully, by people using this technique and making it fail repeatedly, we get some insight. But till then, the jury's out. Thank you for the question. Yes.
Roshan Dattatri, UT Austin. Thank you for a great, inspiring talk. I really like your idea of compiling to DSLs or runtimes.
Yes.
One of the challenges in doing that is different architectures might have different data layouts, or they might prefer different data layouts.
Sure.
I just want to know what your thoughts on that are, because if you move something to the GPU, you might have to transform the data to work well on the GPU.
That's a fantastic question, because it's exactly the topic which we're tackling in a paper under submission at the moment. So if any of the reviewers in the room, please close your ears. Yes, exactly. So in some sense, if you want to get onto the GPU, you may want to change the data structure, right? If you look at some of these APIs, they need information about the data structures, not in the code, like the number of columns. Some of them need to have, if you call it repeatedly, the marshalling cost is going to be too expensive. So what we actually extended it to have a very small language that actually allows at a high level to talk about all those constraints. So you can actually say, this wants it this way round, it wants the data this way, it wants this marshalling techniques. So we have a language solution to that, but it's not the automatic solution. Longer term, I want to be able to work out actually how the data should be this way around to give you this performance. So what I'm trying to do is put a language in first to answer those questions, but longer term, I'm hoping to abandon it. Okay,
Thank you.
Todd Gamble, Minds of More. Thanks for a great talk. Have you thought about how this applies to maybe more mundane problems? Like, if you're able to swap out APIs for different pieces of hardware, have you thought about how you can apply this to package managers? Where, if I know that a piece of software works with version 1.1, API changes from 1.1 to 1.2, can I fit the thing to 1.2 and get it to just work instead of pulling my hair out?
Very useful thing. Yes, we have looked at that, and the idea is if you don't throw the code away, right? That's the key, and you just use this so that actually, in fact, you have the original code before you cut it out. Then what you do is you go back to the original code and try again. Maybe that's not possible, but if you had an inverse back to the original code, you could do that. And then what we're interested in some of this work is about how far away is code from something. Yeah, so we actually found we did some work with ARM, which are one of our sponsors here. We implemented this inside their code advisor code. And we can say, hey, we think this is pretty much like that, but there's some differences here. Why don't you go and have a think about it? So we're actually trying to look at that problem, a pragmatic problem. Yeah, thank you.
Thank you for the amazing talk. I'm Liang Xu from.
Hi.
I'm wondering about during the idiom management process, or after that, about optimization, making compiler enable the idiom management or disable it. Will this interaction between idiom management and the automation, automatization and automation become like a horizontal problem or some very scenario?
Okay, so just to repeat that, because I think the mic went there. Will optimizations inside the compiler affect the idiom recognition task? The answer is yes. What we do at the moment, we use optimizations as a normalization phase before this, so that we actually apply them in a strict order, and that order is kind of done by hand at the moment, which gets the most chronological approach. If you're not careful, it could get into a form that's going to mess up other stuff later on. That's actually right. I guess the way that I look at it is that you could do this normalization pass to find the idioms, replace it with a call, and then stick it back inside LLVM again, and then it's just a function call that can do whatever it wants to do. So in some sense, we just use this for the very high level replacement strategy. You can then take the thing away with that function call, stick it back into LLVM, and play around with the phases any way you like. So in other words, it doesn't have to be a deal breaker. Okay.
Thank you.
Thank you.